Here's day 2 of circuits. So first of all, let's make sure we know the difference between series circuits and parallel circuits. So series circuits you definitely came across back when you did that in grade 9 most likely. And this is when you just have resistors that are in series. So one after another connected to some battery or some voltage source. When you get this scenario, it's very easy. Just add them up. R1 plus R2 plus R3 plus R4 and so on and so on and so on. For ones in parallel, so a parallel circuit, something like the following. So we have resistors in parallel with each other. It's a little more complicated. So it's 1 over R1 plus 1 over R2 plus 1 over R3, etc. And then you have to do one more inverse value because that's equal to 1 over R total. In math class, you may recall doing questions like, oh, you have Johnny paints the fence in 20 minutes and Joey can paint the minutes in 30 minutes. But how long does it take them to paint the fence together? It's solved in the exact same way. So when two things are working in parallel with each other. So example of a typical circuit diagram. So here's just some examples. So we'll go over the types of components that you may see. But here's just some examples of circuits, and we'll be learning how to solve these in the days to come. So for example, this is a circuit. Let's draw more complicated than that, just add a bit more. So you notice I put this plus and minus right here. So again, we're doing conventional current in this class, or again, listen to your teacher. But if you're in my class, we're doing conventional current, so the current's going to flow around. So there's two things that you learned about in circuits back in grade 9. Is that we get these things called nodes and junctions. So when current enters a junction, so current's going to come in through here, and then it's going to split. So some of the current will travel downwards, and some of the current is going to travel to the right. So let's say we originally had like 5 amps of current. And then I measured it with like a voltmeter or ammeter or multimeter, whatever you have, and we found that's 3 amps. That means all the current, like we know this one has to be 2 amps because all the current into a node or junction must equal the current out. Like charge is conserved. And those 2 amps are going to reach over here. And again, because there's 2 paths, 2 goes in, 2 must go out. How much? Well, it depends on what resistors. So I say 0.5 amps go this way, therefore I know that 1.5 goes in this way. Again, right now I'm just making up numbers just to show the different concepts. So as these ones recombine over here, 0.5 plus 1.5, it becomes 2 again. So right here it would be 2 amps. And that 3 plus 2 will become 5 amps right here. And the amount of current passing through the battery, it's still 5 because current does not change as long as the path is constant. So when you actually visualize charge moving on the circuit, you want to kind of think of it as this like long line of, well, just think people in a line. It's not just a single charge moving or a single clump. There's electrons that just are back to back to back going along. So what happens if one of them moves, it causes the next one to also move. So they all move simultaneously. So charge is filled all the way around. Every single place where there is like that wire or resistor, there is charge there. And they're just being pushed along, pushed through. So the other thing is, what we can know about is for voltage. So I'll do this with show voltage on this other diagram. So here's just another. Let's just make up a circuit. And let's put a light bulb there. Let's have a switch. Put an ammeter. Okay. So this is a circuit, and when you do circuits, you should have a ruler. But I'm just drawing right now, so you should be redrawing it with a ruler, make nice straight edges, 90-degree corners. So for voltage, so batteries supply voltage. So for example, let's say this is a 6-volt battery. If you follow any path if I gain 6 volts, following any path, it should use up 6 volts. So if I follow this path, it needs to go from 6 volts back to 0. And then I get 6 again, and back to 0. I get 6 again, back to 0, and so on. Now if I follow this other path over here, like all the way around, same idea. So tracing around, so 6 volts and back to 0. So what this means is, let's say that this first resistor consumed 4 volts. So how I write those plus and minuses like this one. So we think of as the battery gives us potential, but this resistor is going to take away potential. That's why we have those positive negatives are flipped around. In this previous drawing, we would draw our positive minuses like so. If that's 4 volts, that means, like in this first path, I gained 6, I lost 4, and there's one more resistor. In this case, it's a light bulb. So this has to lose 2 volts. This one also has to lose 2 volts. So 2 key ideas in circuits, which you hopefully have encountered back previously when you did circuits. Again, energy, charge is conserved when it enters a node and junction, but for potential, the voltage gain must all be used. We can't just use some of the potential. It has to always go from what you have to 0, and then you get it back when you pass the battery again and back to 0. So it's always using up all that charge each time.